some of my thoughts regarding the second project that Azi had presented. Um, how and why we have come up with this system to measure the distance. Um, because previously the project scope basically entails that if we know the driver behavior from the microscopic driver parameters, that, like, for example, your accelerations and decelerations that you can get from other regularly available sensors. For example, we were fortunate enough to use the car OBD port to get the acceleration data or the engine RPM information from the car's computer. So the car itself has a lot of sensors in it, and we could get those information. But sometimes these informations were not enough. So the basic reason we had come up with this setup is because we wanted to see how, if we had a LiDAR sensor in addition to all the sensors that we had used before, then co-location of these sensors can give us more information than just one sensor. So, for example, if you, as he had pointed out that clearly, that when you want to know what is the relationship between your change in headway with the amount of lateral acceleration that you are making, or what is your behavior when there is a car that is beside you, around you. But obviously, like, this whole project, the way that we have thought that this sensors would work for us, it doesn't work that way, and we have some noises all the time. And so basically, when you go through that process, and especially if you are doing also a sensor project yourself, you will find that having a proper way of storing the data is probably the first challenge before you could analyze the data and have a method to throw out the noise or error from the data. So in this case, we use the date and time as kind of the tagging or the kind of combining parameter. The use of a real-time clock was really important in here. Obviously, like, we haven't quite gone through all that process, but what the real-time clock should do is to sync all the data that is coming from different sensors and have them a consistent timing parameter, which is really important because and some of these sensors are giving you data at different resolution. So some sensor is giving you at 1 hertz, some sensor is giving you at 1000 hertz. That means how, if you see an interesting event, a hard acceleration or hard deceleration event, how are going to compare from one event to another? Only the time is our only way that we can tag back from one to another. And one thing we didn't add here is that we also had the video with the feed. Specifically, like, it's always, we find it useful to have video feed. So, like, whenever the data recording had done, and you could always go back to the video and see what had happened at that time. Okay, so the second part of our presentation today, so I am presenting on behalf of our team here. My teammate Beza Dagdas, he could not be here, but he and me, Thomas Chase, and Dr. Nagy Rafael had worked on this project for about more than 2 years now. So we started late 2015. The whole plan, so the task we had, and it's the Department of Energy funded project, that they wanted to know if you could provide incentives and information to drivers or trip makers, then if that would have reduced the amount of energy they would consume. And we know, like, there are a lot of decisions involved in how you could reduce in your energy consumption footprint. So for example, if you use a car versus if you use bus, definitely you had made a lot of difference in the amount of energy you consume. And then like if you use a hybrid car, or if you use like a big Hummer car, then your fuel consumption is different. But one of the low-lying fruit that we think that we could really target is that how you drive. So it doesn't depend on for you to change your mode, for example, like you moving from a car to a bus. Or it doesn't depend for you to change your route, like you use a different route. We targeted specifically that part where you wanted to see if just by changing how you drive, like how much pressure you put on your pedal, or how much hardly you put your brake on, that kind of thing, if that is going to impact your energy consumption. And to see that, we kind of use this technology that we had, the I2D data, and today I'm going to show some more application of this project. Specifically, if you see this, this is like the whole package here. You have a box where there are some sensors, and that box is connected to the vehicle, and the same technology, the OBD technology, is here. Data, you can store the data, and I'm going to go through that later. And then there is some communication system. So that data that is stored in this box could go to a cloud server, or someone could access the data remotely because you're sending this data somewhere else. Okay. So as I mentioned, the car itself, it shows a lot of sensors that is inside that car. And I think modern cars have even more. They're putting more sensors in there. And all these cars, most of them have multiple computers. Some cars may have single computer now, but this information is being stored. Some companies may have put already communication devices in your car, so that when you go for engine checkup or like regular checkup, they might download this information from your car, or they might do preventative maintenance, like they automatically take information from your car, so that you may not even know that that information is being transferred. So it's all in the fine print. But the way you could access some of this information, like if you have an engine check light, then you sometimes go to the mechanic and they will put some device on your OBD port and check, like, okay, you have code number XYZ. So that information can be accessed from this port that is sometimes like under the steering wheel, you could find that. So what we did, along with our partner in Portugal, who kind of built this system for us, so we tapped into that port, and we said, if we put some additional sensors, like if you put a GPS that can give you the accurate location, if you put an accelerometer or 3D accelerometer that gives you the lateral and longitudinal acceleration, and vertical also, and the altimeter, and then we put some simple processor, because the data that is coming from the car computer is huge. It may come at sometimes 100 hertz rate, sometimes 10 hertz rate. So you have to sample it down to make it like reasonable for communication, because it's going to be real-time communication, and if you put too much burden on the communication line, it may get jammed and the memory can get full faster. So we process the data down to a like 1 hertz. So this case we transmit data at 1 hertz resolution, and then we transmit the data using a cellular network. So you can see here the data basically comes from the sensor to the port through the device, and Live Drive along with E3, we have a cloud database where the data is stored, and there is a web platform where the drivers could access how they have driven, and we could add more analytics to it, so we could give them suggestion how this would work. And in the down, you can see like whole range of sensors and communication system that goes inside the box. So just this slide is just here to say like what is the difference between a I2D system with your phone sensors. And of course, the phone itself, the problem of having multiple sensors running all the time in a phone that you have, it has some excellent sensors in it already, but some of the sensors drain your battery too fast. And that may be something that you may miss a lot of information. And to avoid that, what cell companies or the phone manufacturers does is that they give you the option to turn off. Let's say you can turn off your GPS all the time. So sometime, so you may not get all the data that you can get in your phone. And specifically, this one has kind of a communication. I know some of the phone apps already have this communication, like if you're using Strava or like if you're running, like Fitbit and type of softwares, you could get like, yeah, you did great, you ran like 10 miles last week or something like that. But specifically with this system, you could do that. You could talk to the people. And we had tested some of the VIV. So this term, I think you all probably know about that, is like the communication or the connected vehicle technique. Is like one type of technique is you do V2I. Basically, you have some data in vehicle, you send to infrastructure, they don't talk back. There is other one where you send some information and the infrastructure also sends some information back. So we had tested, that's called VIV, vehicle to infrastructure to vehicle. And we tested some of the interface, like for example, this I2D device, we could also add a Bluetooth sensor in it. So that Bluetooth sensor, when some information is coming back here, we could transfer that information into your smartphone that is in your car, or into the panel of your car, which has a Bluetooth enabled system already. So that means it's both way, the communication is both way. And so that's basically what I told is VIV systems are more comprehensive than just the standalone V2I communications. Okay, so just to summarize what kind of driving behavior data we can get. And obviously, like all this data is coming from different sensors, but it depends on the analyst for us to define how you can relate it to actual driving behavior with the sensor data. So in this page, it shows if you log on to that system, you could say like in the last 7 days, what was your overall scores? Obviously, you can define your score in any way. In our case, we defined it using how much energy efficient you were, like eco driving, how much safe you're driving. So like as you know, like some of the insurance companies are already giving their customers the way, like they could track your micro scale behavior, driving behavior information, and they could give you a score, give you some discount on your monthly insurance or yearly insurance, something like that. So that's your safety score. And the last one is comfort. It's defined basically by how much jerk or vertical acceleration. So if you are like driving on potholes very fast, that would mean like you'd have jerks very sharply, and then that information is there. So we could combine this information to come up with an overall score. This page specifically is very interesting in the communication portal, is that, for example, you had done a trip. So someone had, of course, this is privacy protected. And you can see, like, obviously there are some reasons why this is privacy protected. Not everyone should see where you started your trip and where you ended up. But you can see your trip. That's fine. So when you log in, you can see where you stopped. This is just the stop view, but obviously there are some other information like weather event, how much fuel consumption you are doing, how much delay you did, and all this information you can show on this dashboard. And what is specifically interesting, if you look at the right graph, is that you can see your behavior or driving style, you would say, with time, like how much acceleration that you did here, there is information about lateral acceleration, your vertical acceleration, all this information on here. So you could really see how you were doing. And so in ITRI, we have about, since April 2014, we had about like more than 50 volunteer drivers so far. And that varies because some people agrees to volunteer and some people leave. So yes, the pool is varying in driver numbers. But I think at one point we had maximum 32 drivers. So it's just one point. Each sensor or each package sends data for every second. So we have gathered about 68 million seconds of data, and that's driven in different kinds of roads in North Carolina. 568K miles of driving behavior. All the data we have archived in a server, and of course, like if you are planning to use connected vehicle information later on and this kind of information, these are privacy protected information. So we had to go through a very complicated institutional review board authorization, or sometimes it's called the IRB authorization process. And to get that, we had to say that it is stored in a very secure place. No one knows. It's anonymized, so no one can track back, and we would not publish this information anywhere. So it's a responsibility from our side to how we manage and curate this information. Okay, so this first case example is where we try to say is, because this is a very temporal and spatially tagged information that you get along a large footprint of area. So you can say like, what is your true free flow speed? And if you have the ACM equations. So for example, we try to feed 3 different model form to model the free flow speed at different locations. So we have this data, and we looked at how these models performed. And this model actually, like the third model, where you use the posted speed limit and the section should be ramp density, that has sufficiently good fit. So at 0.576 is not bad compared to the current ACM 2010 model, which had a lot more error. Like I agree that it's not comparing apples to apples, but we had the paper, so you could see that how this is performing. And then the other example where we looked at the free flow speed estimation for 2 different type of drivers. Like say, because we know which drivers go through the roads every day or not. If that driver is going through that road, I think more than 30 times a year, then we call him a familiar driver. If less, then it's unfamiliar. And you see here, like at 65 mile per hour freeways, the familiar drivers on average drives at a faster speed than the unfamiliar driver. But the scenario is kind of opposite on the 55 mile per hour freeways or highways, because we think that like familiar drivers know at what speed to drive and not be caught by the police. They also know where the speed goes from 65 to 55. So they kind of drive at that sweet spot, like 65, they always drive at like less than 75 range. And then 55, they always drive less than 65. So that kind of confirms how different people drive at different conditions. This is another example where we looked at the crash propensity estimation. So basically, it's just used 3 months of I2D data at different locations, and we looked at crash data from the NCDOT crash database, and we looked at what is the correlation of the real crash that is happening at a location with the percentage of time there is happening, there like high deceleration events are happening over there. So the deceleration information is coming from the I2D data, the microscale behavior data, and the crash data is coming from the crash database. And we found a very significant correlation that 85% of the rear end crashes, like rear end crashes mostly happen where you don't have enough time to react, so you could stop. So that occurred within the hotspot that we already identified from our I2D data, which is like a very important finding. The other one is how you measure drivers' aggressiveness as a function of surrounding traffic. So basically, in this case, the microscale information is used along with the probe vehicle data that we get. Like for example, INRIX or RETIX data sources. You could use the speed that or travel time that you get from INRIX or RETIX data sets to come up with, and using some other like volume and density information to come up with the level of service. And you look at different level of service condition. What is the relation of your lateral acceleration that you get from I2D device? This is interesting. Like for example, if you are at level of service A, that means it's kind of free, like you can move freely, right? Then your median or average lateral acceleration is lower because you're driving at a faster speed, then you probably don't need to change your lanes too much, right? So you try to stick here. But the range is kind of wide at that point. But you see at level of service C, where it gets a little bit congested, and then people want to, some people or most people want to change lanes. They try to change lanes, and the line goes higher, and the dotted lines are the means and max, and you see that the average is very close to the max. That means most people are actually choosing a lateral acceleration that is very close to the maximum possible lateral acceleration that you could do at that level of service, right? But then if you go to more and more congested condition, then it really gets wide. Like you get two different type of people. One type of people is like they don't want to change their lanes, and some people like they would change their lanes because you see the lateral acceleration, the maximum lateral acceleration is higher. That means that they would take risk to change their lanes. But overall, we see a sharp decline. We see a mild decline. That like people kind of stick to the same type of average behavior after some level of congestion had occurred. So in summary, like this is an interesting data set that we have built over time. The power of this data comes from that this data is already in a database, and we have linked this data with time and people, because we know the driver characteristics, we could know the driver characteristics, and also we have the spatial information. We know where this had happened. So this gives you the power, like the three use cases that we went through, all of them fused kind of an external information, trying to see if your crash data can give you more insight, or what in the crash data you have been missing so far, so you could explain it with your microscale information. So I would say from a sensors and instrumentation point of view, this may become pretty standard, but obviously there is scope for it. So for example, I can go with the history. Like in 2014, we said we used a version that's called version 2, and there was nothing wrong with version 2. Specifically, it had everything, the same thing. But then we decided to upgrade it to version 3, which basically has a little bit better GPS positioning system. So we could know, for example, where that person is without like filtering data too much. But then we are doing a new project now where we want to know how the people's lane changing behavior is with respect to um, different spatial condition, with respect to different surrounding condition. Then this device is not adequate for us anymore. So we need like centimeter level resolution on the GPS. And like some of these GPS are very expensive systems. Um, so yeah, so basically, even though from a sensor standpoint we are at a very standardized situation here, but then improvement occurs with time, and it happens, and we have to adapt to it. We have to adapt our whole analysis system. We have to adapt our whole how we store the data, how we access the data, and everything. Like previously, we didn't have a database in E3. We just carried around CSV files, which is extremely inefficient because if you have gigabytes of data and you want to, let's say, run, Excel cannot do it. You want to use R and you have 16 gigabytes of RAM and you want to load 64 gigabytes of data, you fail. And then like we come up to say like, okay, so now we can go to that other stage. So right now we are working on some other processes, like how we can better anonymize the data even within the database, so we could share this information with others. By anonymizing, we could do many things, like we could de-identify the sensitive locations where people had really traveled during their trips, or we could filter out some places that if you know that this is already sensitive information. So we are trying different ways how we can share this information publicly. And then other potential is that if we could share information as that thing is happening. So this is like streaming data. So if you could give API access to people to download data directly from our server or not. Yep. Any question? Yeah.
Could you go back to
Yeah, sure.
example one?
Yeah.
Next.
Oh, sorry.
Can we verify if the difference between two grams is really significantly, statistically significant or not?
Yeah. I cannot tell about this one because I was not the author of that paper. They didn't make me the author, but that's fine. But I can tell about the data in general. So what happens is that since at one time we have, like, let's say 35 drivers at some point, and if you take a section of road, most of the time that section is dominated by one or two people who is mostly traveling that route, right? So that's a problem in terms of determining significance, because you are trying to say this is the representative curve for a familiar driver, but you're taking 80% of the data from two drivers. That's not representative. Okay, so if let's say we had 200 devices running all the time and we have more than 30 drivers running at one type of system, so let's say we solve that problem. But even after that, you're right. How would you say that the difference among these two drivers groups are significant? You could do some statistical test after that system, like case test or something like that, to say if that difference is significant or not. But then again, another question, whether the threshold that we use to differentiate familiar versus unfamiliar driver, is that a good threshold? Is 30 trips a year a good threshold for familiarity or not? Maybe or may not be. It's up to the researcher. So we could move the needle, see how much difference you get, and try to see if this makes sense or not. But in general, this pair of graph kind of makes sense to what we expect. So, yep.
I have
Yeah, sure. Yeah, no problem.
Is there any relationship between the safety of the example 2 and results of example 3? I think there might be, because the lateral something,
Lateral was on number
Yeah.
3. Yeah.
it, it might be correlated to the safety of certain section.
So, in this paper, Taizin looked at just rear end collisions. I think most of the rear end collisions, because it's correlated to your